Webinars now means, and we have touched upon a couple of concepts in diffuse optics. Today, again, this will be a reinforcing class. I will just go through again the concept that has been said in the past. Bit more practical means I will try to trigger a bit of scientist or the inventor inside you, and also a bit of introduction to the biophotonics box that you got to you. Means I will not go through step by step of what to do with the box because you already have manuals for that. Here I will be focusing more on is what you can exploit with those boxes for diffuse optics to understand diffuse optics better. Okay, let's start. So first things first, I hope the presentation knows. Yeah. So to understand diffuse optics, we should understand what linear optics is. And so in linear optics, you would have already read in your high school, probably in your bachelor's as well. You have light, it incidents, and it can reflect, that is specular reflection, or it can refract. That means the light can get through a transparent medium. Means if you're coming at a certain angle, it can totally internally reflect depending on the refractive index of the medium and the internal and external medium. So this is what we learned in linear optics. So that's fair and good, but diffuse optics is something different. I would like to show you pictorially here. So in linear optics, you send light, it just takes one straight path. But in diffuse optics, you have so many scatterers, the light takes multiple paths and it's hard to judge which path it is. Because in reality, it looks something like this. In clear medium, when you send a laser, it will go just straight and you can see it goes straight and there is a little bit of scattering. But if it is a diffuse medium, like you take the water with a drop of milk, it will form this kind of bulb. That means the light is getting scattered everywhere and it's no more traveling in the straight line. And here is a very good example. Means there is water and drops of milk has been systematically added. So when you have very little milk, and you can see a laser that goes through, and as you increase more and more the concentration of milk, the scattering increases, and eventually you don't have light that goes through, but just a kind of shape of sphere of bulb glow that you can see there. That's because of diffusion. So what? Why diffusion is very important? Because everything across us is diffusion. You would have seen clouds, right? Did you ever wonder why the cloud is white though the sky is blue? The reason is diffusion, because the cloud contains a lot of droplets of water, and this water just redirects the light coming from sun in all directions. That's the reason why it looks white, because it reflects all possible light, all possible wavelengths of light. And you would have seen foam in sea, that's also looking white. You would have had a vacation, unfortunately not now, but you can have maybe within next month. If you see foam, you can wonder why it is. It's again because the foam has multiple droplets, because it smashed against water, smashes against each other, and it forms foam. This foam looks white because of multiple particles of water that diffuses light. And you see the leaf that is green, again it's because of diffusion. We humans are white, that because of diffusion. So anything that is not transparent but it looks a certain color, that's because of diffusion. Means when it looks color, simply because it absorbs all other wavelengths except that wavelength. That's why a leaf looks green. And if something else looks red, for the similar reason, it absorbs all the wavelengths except red color. So as you see around nature that we see across, and the beauty that we see across, it's all because of diffusion. So by gaining significant understanding of this diffusion process will help us to understand the beautiful nature that exists across around us. For us, it's more important in biophotonics to understand how the light behaves inside the human body. So that's the reason why we are trying to understand diffuse optics and trying to build models that we could accurately address diffusing media like human body. So I will try to make a pictorial view of what things look like in a diffusing medium. So in a typical linear optics, the absorption is nothing but absorption of the medium. The light travels straight. But in diffuse optics, So you have incident and you have specular reflection. That's kind of similar. And you have refraction, but the refraction can't get across the medium. It just stops there. So that's because you have scattering, then the light takes a certain path, and you have again scattering. So one thing that can happen when you send light through a diffusing medium is it can scatter across multiple paths. And if it is lucky enough, it won't get lost in the medium, but it will find its way out. And you have the light that is coming out. That's one phenomenon, that's scattering. And the second thing is absorption. So the light just gets in and it has multiple scatterings. It scatters for sufficient amount of time that it gets absorbed. This is another phenomenon that can happen in a diffusive medium. The third thing is, again, it has multiple scatterings. Instead of being absorbed, it's going to get reabsorbed and re-emitted because of fluorescence or phosphorescence. So the light gets absorbed within an atom and it or a molecule, and it gets re-emitted as with a shifted wavelength as fluorescence or with a delayed phosphorescence. So these are some of the simple things that can happen when you send light into the medium. In any case, light is not going to travel straight. All the time it's going to have scattering, and you are going to have absorption, scattering, fluorescence or phosphorescence depending on what's going to take place and which is dominant. For our rest of the presentations, I would just say that the absorption and scattering dominates in our tissue. And most of the times we do have fluorescence, but it's really a smaller amount. So we will just ignore fluorescence for a while and keep in mind absorption and scattering. We need to understand how it behaves. So said this, I will take a step back. Okay, the other thing that can happen is transmittance. As you see in linear optics, the light just gets through, but in our case, the light, if it is lucky enough, it can go across without being absorbed, without being converted into fluorescence or phosphorescent light. It will just get out as a transmitted diffuse light. So said this, I just want to take a step back. I want to just get an inventor inside you. So let's say, I don't know whether you know Beer-Lambert's law. It's a law that defines how the absorption happens in a medium. Let's say the beer didn't exist in the planet, means he invented it some few centuries ago. Let's say he wasn't there and the absorption laws weren't invented, or you belong to a time where the Beer-Lambert, before beer, and you wanted to understand how the absorption happens, okay? So there is a practical way to understand it and model it. So this is a kind of the curve. So you send light into the medium and you observe in the beginning when time equal to 0, or when the length of the medium is 0. You see, you send I naught light, and through the medium, the light is going to get decreased, and you observe that it is following an exponential behavior. So we can simply say, okay, you have I1, that is the light that you have observed at the output, is nothing but I naught divided by exponential to the power some x. Okay, it should be a negative sign over there. So I naught is, or in the other way, means it's I1 is equal to I naught times e to the power minus absorption times length. Okay, so it's exponentially decaying function. And this is what you observe, and then you try to define a phenomenon. You try to see when the intensity of the light becomes 1 by e times. Okay, 1 by e times, that is when length of the travel by the light is equivalent to 1 by absorption, that is when our absorption is equivalent to 1 by length of the light, 1 by length of the length, 1 divided by the length. You see that that the light is lost by 40%. So simply you have attenuation of 37%. So when you say absorption of 0.1 or 1 centimeter inverse, it simply means you will lose 37% of light when the light travels into the medium by 1 centimeter. That's what it is. So this is something like this, means anything that you observe experimentally, you try to model it mathematically. And when you try to model it mathematically, you understand it is going to follow an exponential phenomenon. And then you give defined a coefficient that what you call it as absorption. Then you see when the length of the traveled by the light is, when you multiply that with absorption, means you get 1 by E value, that is 40% of attenuation. That is when you say, okay, the absorption of light equal, means the length is equal to 1 by absorption value. So set this means this is that simple, but you can complicate it a bit more further. That's what you have it here. So you can define by using a differential where you send light I naught at any given point of time. You have IZ light. Then you have an attenuation over DZ, a thin infinitesimal surface. And then you find out what is Iz. It's nothing but after this infinitesimal surface is Iz minus dl. That is attenuation that happened due to the length it traveled through this small surface. And if you differentiate again, you will get back the Beer-Lambert's law. So in either case, you can understand that how the Beer-Lambert's law works. The simple absorption could be just simply explained as, if it is 1 centimeter inverse, that simply means at the length of 1 by E, that is 1 centimeter, you have 40%, close to 37% or 40% of absorption of light. So that's how the absorption works. Now let's get to scattering, what happens in the diffusion medium. So as I said, you send in the light. Now it can take multiple paths. So, and if it is lucky enough, it gets out. There is 3 different case study here. In first case, you have few scatterers. In second case, you have multiple scatterers. And the third case, you have even more. Okay. So said this means in first case, there are more chances for the light to get across simply because it's going to face only few times a scatterer. In second case, it's going to reduce considerably. In third case, it's going to be very hard for light to get across simply because it's going to scatter multiple times before it comes on the other side of the medium. That means it can get absorbed or it could get diverted and get out of the medium. So for such a situation, that's how the light looks like. Means you send in the light. In first case, you have more light, really lot of light across. It's going to be like a sphere because it's scattering all the time. And in second case, it's going to reduce considerably. With distance, it's going to reduce the intensity. In third case, the intensity is going to reduce even more. So my previous supervisor used to explain this in like this. So let's say you are in Washington Street in Cork. I hope all of you from Cork. So Washington Street is one of the famous streets in Cork. And let's say I got 100 people and I just left them to ask them to move randomly towards railway station. So railway station is located close to 2 kilometers from there. If I try to observe how many people are there at St. Patrick's Street, which is just 200 meters away from Washington Street, probably I will find close to 30 or 40 people. Means let's say all these 100 people are not from Cork. That means they don't know how to reach railway station. I find only 40 people at St. Patrick's Street simply because there are so many cross streets at Washington Street. People will think moving in this direction I might get to railway station, or move in other street might get to railway station. Eventually, they are getting scattered everywhere, and the scattering will depend on number of junctions that you have. So in our medium, the number of junctions is nothing but number of scatterers. Okay, and on the other hand, let's say I am going to have less number of streets. Means I'm going to leave you again at Washington Street, have a minimum number of streets to reach till railway station, in which case I have really minimum number of scatterers. It's highly likely I will see more than 40 people at St. Patrick's Street and close to 30 or 40 people at railway station even, simply because the number of streets that I'm going to see is lesser and lesser. Number of streets that I have is lesser and lesser. That means less possibility for people to get distracted and lose their path. It's similar thing that happens in a diffusive medium. So as you see, in first case, you have less number of streets. As you go across, you have more number of streets. That means more people are going to get lost, and less people are going to travel across and reach the railway station. So that's the scattering phenomenon. And with this, I'm just going to leave you to explore with your biophotonics kit. So one of the things is, awesome thing is how to make a phantom. And there you can tailor the scattering to the way you want. You can simply increase number of scatterers by adding more milk. That means you are going to increase more number of streets. That means you are going to distract people to not reach the destination. So you also have a demo kit where you have built RGB, red, green, and blue LEDs. You can simply make a scatter, a phantom with different scattering coefficient, that is different concentrations of milk. And you can keep it on top of the red LED and you can see what's going to happen. That's one way to see how number of photons is going to decrease more and more by increasing the amount of scatterer. Or we already know the scattering is increases a lot towards blue and decreases when you reach to red. This is because of the Rayleigh scattering, lambda to the power 4 behavior. So when you keep the same phantom on top of RGB light, with blue light, you can see the photons are getting attenuated much more as compared to green or red light. So there is one more way to understand how scattering is going to reduce the light that is going to get across. So we can simply say in first case, you have too many streets, here less streets. In case of red, you have even lesser. And other thing that I want to point out to you is when you think of diffusion, it's not scattering happening uniformly in all directions. For example, when you look at sky, the blue color of sky is because of Rayleigh scattering that happens in all directions equally, irrespective of the direction of the input radiation. But on the other hand, the phenomenon, that's why it looks blue, clearly blue, simply because it purely depends on lambda to the power 4 phenomenon. That means blue light will scatter more. That means you will look, the sky will look blue. On the other hand, the cloud follows Mie scattering, means especially when you have the size of the molecules, or if you have a droplets of water, which is of the orders of micron, molecule is nanometers, but you have micron sized droplets, which is the case in terms of when you have cloud, the light is forward directed. You can see here an example. I send a laser light into a drop of milk, water with a drop of milk in it. You see most of the light is going forward. If it were to be Rayleigh scattering, you won't see this line. You will just see everywhere equally distributed like you see in the sky. So the Mie scattering is forward directed. When we say that when we try to measure scattering, it's never going to be the scattering, actual scattering that we will observe. What we are going to observe is a reduced scattering. More details about this will be explained by the forthcoming tutorials and the computer lab exercise. I will leave it here. And it's dependent on the G factor, which simply describes how forward directed your light is. The other concept that I want to just emphasize means we separately learned about absorption and we learned about scattering. But in our diffusing media, like our skin, both of them are going to take place together. That means you have to account for absorption and scattering together. That means you don't have Beer-Lambert's law, but you will have something that is modified. And the absorption coefficient is not only going to have absorption, is going to take into account absorption, but it's also going to take into account the number of photons being lost because of scattering. So the formula looks something like this, but more details you will find in your next set of courses during your computer lab exercise tutorial. The next concept that I want to just pitch you in is that means when you have diffusive medium, means depending on the scattering, we saw already the light can penetrate deeper or shallower. This has an effect on the penetration depth of the medium. For example, if you have your skin or your body highly scattering, that means the light can never ever reach a inclusion in this case, but let's assume bone. So when you have really high scattering, the light can never reach bone. But if you have lower scattering, the light can reach deeper to the bone. So this is what it is. Means that's the advantage if you have a lesser scattering. For example, some parts of the body are least scattering. In that case, you can penetrate more deeper. That means that those places are more transparent than you think of it. This particular phenomenon of whether being transparent or not could be explored by by a set of exercise means or by exploring your biophotonics kit. For example, there is an exercise or a way to create a phantom with different inclusions. That means you have the same phantom with the same scattering coefficient or with the range of scattering coefficients, and you will put a kind of inclusion at particular depth. That is, you will put a black bob or something. This kind of simulates tumor. Then you can play around with light to see how well you can distinguish tumor by increasing the absorption or scattering. Absorption by adding ink, scattering by adding more milk. With this, you can try to make some observations means, and try to get an intuitive feel of how scattering and absorption is going to help you, or is going to make it harder for us to see any tumor deep in the tissue. If you want to become more accurate, you can use the app, the PHOEFOX app, to accurately quantify the absorption, means the light attenuated across these inclusions, and try to make a plot and understand how different scattering and absorption has effect on attenuation of light. With this, I just going to leave you with some questions for you to think about. Means, for example, you have the light, white light, you put the hand on top. Then what happens? Means the white light becomes red light. Why? Why it's not blue color? Because white light has all color, right? Blue, green, and red. So why it's only red color? Just think over it. And why can't we see the shadows of bone? Means we should be able to see shadows of bone, right? Why we don't see it? Again, think over it. Probably we will ask you again, means or drop us a message on what are the answers that you think for this particular question. And here is the hint. I just want to tell you again that we have blood that is means blood that below 600 nanometer that absorbs all the wavelength below 600 compared to above 600. That is blue and green. So with this, I just want to conclude. I want to thank you all. Thank you, Marcelo, for this opportunity. And I hope you got some picture of how diffuse optics work and different phenomena that happens in human tissue. And all that I would just emphasize now is just think intuitively how to model these different phenomena that happen in tissue, diffusive media like human tissue. It would be great if you could come across with some new thoughts, and if you have anything that you would like to discuss regarding this concept, we are here for you, either now or through mail any other time. Thank you.